It's my great pleasure to introduce Zach Pertl, who is now the Center for Science Policy at Arizona State University. He has spent a lot of time at NASA studying engineering, and he also is one of the primary movers of the Forum on Philosophy of Technology, uh, uh, philosophy and technology.
Forum on
And
Philosophy, Engineering, and Technology.
of
FPET.
engineering. I knew I was missing something. Sorry. From philosophy and engineering and technology, or FPET. Uh, so he has a lot of experience in terms of how complex engineering takes place, and he's also a philosopher. So it's my great pleasure to have him in this lecture series. Zach, please check your slides and we will proceed.
Thank you all. And my metro train skipped its stop this morning and went one stop too far. So I'm getting in later than planned, but very excited to be here with all of you and very excited to talk to people around the world. And I took the liberty of inviting my very dear colleague, Martin Stacy, who's collaborated with me along with this work with a few others. And so I am going to share my screen. I'm not able to do dual display at the moment, unfortunately, since there's something wrong with my speakers. But let me. So I have just recently joined the faculty at Arizona State University, but I'm based in Washington, D.C. I'm the director of our Consortium for Science Policy and Outcomes. And the talk that I'm going to give today is called Engineering Knowledge for What? And it's assessing Walter Vincenti's categories of knowledge and their prospects for engineering practice. So I have been, my PhD's in systems engineering, and I've had a degree in philosophy and a lot of research publications in philosophy. But as Sub alluded to, I've spent most of my career working professionally at NASA, including on systems engineering lifecycle reviews, which are wonderful moments where you try to bring everything together and understand the health of a system. By the way, can I do a sound check to make sure you're hearing me okay?
We can hear you very well.
Good. So most recently, I've been working on our commercial lunar payload services, the commercial lunar landers. Got to have some really excellent experiences through that. The work that I'm doing at CISPO is going to have a significant amount of research focus, and I'm excited to keep doing work in ethics and epistemology of engineering, as I'll talk a little bit about more in a second. So, but I am, I will not talk as much about the NASA examples that I've worked on in my career, but there's an orientation in my work to think about both how real world projects, as well as the policies that shape those projects that are supported by government agencies, how that shapes activities. So now there's one thought conversation on the linear model of innovation that is going to be sort of a target of mine in today's conversation, and that I think is in some ways very central to this question of engineering knowledge, but in other ways is also orthogonal to it. So I'll describe the linear model of innovation a little bit later, but the concept is that there's roughly that the sort of, as Vannevar Bush once said in the major science policy report from 1945, that the fruits of practical endeavors doesn't come from Yankee ingenuity anymore. It comes from people developing basic research and coming up with new science that then is used by engineers to do different activities, and to do the work that they do. And there's often an implied focus in the literature about scientific laws being important for the function of engineering. Which, if I know that there are a lot of engineers on the line here, I think it's sometimes interesting. While you can pull scientific laws from textbooks, the extent to which new laws are enabling breakthroughs in scientific and engineering practice, I think, is a debatable topic. But the engineer Walter Vincenti has a set of categories of what he describes as examples of engineering knowledge that I think are at least existence proofs that there's engineering knowledge that is emerging directly from practice, that is not following this linear model of engineering. And I also think that there is great value. The engineering knowledge, there is a so what as to why it matters, because it gives engineers a vocabulary for talking about their own knowledge generation processes. I think that at NASA, for example, there's lots of knowledge management processes, but a lot of them don't really touch or are not salient to the actual technical work that engineers are doing or about the uncertainties that they think about. Um, I do know that there's a lot of scholars here, and Sub has talked to me about CK's concept of knowledge theory, another work in design studies, but I've not been working to integrate that work today. I've been following this literature strain from Vincenti. Um, but I think the big picture goal for the talk is I do want to try to help convince people here that there's ways in which bad epistemology or bad conceptions of how we know what we know, then that if you try to force bad conceptions of epistemology onto engineering and onto management, that it can lead towards bad outcomes. So I do think there needs to be a lot of empirical work on this. This can't just be armchair philosophy, and I've done some of that empirical work that I'll allude to a little bit later. But this is the direction that I want to go for today. So you're going to learn a lot about Walter Vincenti's categories of engineering knowledge, a little bit of philosophy of science on why this linear model is not quite right, and then trying to frame through an emerging agenda on this. So a lot of the work I'm talking about today, it's a bit experimental. I do have a book on engineering knowledge on contract that I'm on, and so I'm trying out and experimenting with some new ideas today. Um, so with that, I will start talking about Walter Vincenti's work on engineering knowledge, and I'm drawing off of a presentation that I actually first worked with my colleague Martin Stacy a few years ago. Um, so what is knowledge in engineering, and why do we care? I think many people on this call naturally gravitate towards it, but it's still, despite pockets of knowledge, of research, say in knowledge management and systems engineering itself, and the philosophy of engineering, um, it's, I would argue, under researched, and it's hard to connect that research with practitioners. There's a number of philosophers who've engaged with this question of engineering knowledge, but a lot of that literature is in some ways stopped or paused since 2009. I do think that from a practical sense, that many engineers, the activities that we do is to create data that you need in order to systems, so creating wind tunnels, performing tests and validation about how a system works. I think that engineers really care about like monitoring and recording, especially for the formal knowledge management processes that I alluded to that NASA has. Um, and so funding actual work to sort of capture what people know, writing down lessons learned, and trying to share them. You can also care a lot about engineering knowledge if you're an educator, because you want to figure out what is it that you actually need to teach your new engineers. There's also competent skills that are a part of education as well. Um, but I think at the end of the day, and especially if let's say if you're someone involved in policy from an agency, if you want to do something ambitious, you need to know how to do it. And that to build new things, often knowledge is needed. And sometimes it's new knowledge, sometimes it's rediscovered, and knowledge matters. So Walter Vincenti actually began his career at the predecessor to NASA, the National Aeronautics Committee, and he ended up becoming a professor at Stanford University and had a great deal of work, sort of integrating aeronautics research and the history of technology. And he um, was once asked by the famous economist one day, Nathan Rosenberg, he asked, like, "What is it that you engineers do?" And Vincenti sat there and thought about it. And I need to give you a good answer about that. And I feel like a lot of what we do depends on what we know, and it's hard to sort of describe what this is. So Vincenti ended up writing over from the late 70s into the 1990, a series of work and historical case studies that ended up being part of the book, What Engineers Know and How They Know It. And he really goes so far as to say that engineers create knowledge that is separate from science, that engineering knowledge is separate. I plead agnostic to this. I think that engineering shapes many outcomes, and um, its unique context is certainly deserving of study, independent from any broader context of what science might say. Um, uh, but he does develop these categories of engineering knowledge based upon his case studies in aviation and industry. So the these are the categories. I'm not going to go into them in detail. I want to give you a flavor of them, and I think you can read them and gravitate to some of the points. Um, so and I've got references that I'll share as we go along the way here. So he lays out, so for example, fundamental design concepts. So this would be, what is the sort of like concept of an airplane? What is the concept of, if you were to like look at an artifact, what is the fundamental concept of a chair that we're all sitting in, or maybe some people are standing? Um, and he argues and ties this that every device has an operational principle, and it's about how the characteristic parts of that device fulfill their special function, the sort of form fulfilling function. And so, uniquely to focus on what is it that uniquely makes an airplane work is that you can have airflow going over a wing of an airplane, and there's a difference in pressure between the air on top of the plane and the air on bottom, which causes lift. And so the focus there is to make a surface support a given weight by the application of power to the resistance of air. So engineers, sometimes when engineers come up with a new design, they are coming up with a new fundamental design principle or concept. Sometimes engineers are just tweaking, like there's lots of cars, you get a new car, but you've got just an incrementally improved car from the year before. But if you look at something such as, and I should have a better example off the top of my head, but if you look at people who are using hydro boosted like water jetpacks at the beach to sort of fly through the air, it's a very different operational principle than what you have in other contexts. So it shouldn't surprise anyone that engineers work with design. There's lots of work that engineers do to come up with criteria and specifications for how those designs should work. I won't go into that in as much detail, but there's also a lot of work that for any engineering system, there's practical considerations. Vincenti has an excellent case study on flush rivets, and that's basically when you're binding together sheets of metal for an airplane wing. You want to make the overall weight of the plane as light as possible. And so early planes would connect the plates themselves based upon putting in a rivet and like a strong divot that would um, protrude out of the wing itself, but would strongly connect the sheets of metal so that the plane would hold and maintain its structural integrity. So, however, as when you have rivets that are bolting out, they create drag and they slow down the plane. So, or as early as flight began, there was a surfaces of an airplane as smooth as possible, and to get a rivet that would basically be flush with the surface, as you see is shown in the. And there were different approaches for creating flush rivets. You can see you can either try to have like a countersink where the metal of the rivet is extended into the back of the device of the sheet itself and helps hold it together. You can actually have a broader dimple where the sheet pops out and basically accommodates that. Um, it was a bedeviling process, and it still is one where of figuring out what to do is dictated by trial and error, trying things, figuring out if it worked, moving from there to implement it in practice. And there was no sort of physics that guided it. There was not enough material science to sort of figure out, okay, you must design the sheets to be of this level of thickness to see how it works. Engineers and technicians had to work together to try a variety of methods and to figure out what's the lowest mass but still structurally secure way to make a rivet that could be installed there. What materials should you use? And like for a given set of materials, what do you get from that? So that's an example where engineers have to come up with something, and Vincenti claims that this is independent of ongoing scientific knowledge. Control volume analysis, anyone here who's taken a mechanical engineering degree would have done a significant amount of work in looking at fluid flow through pipes, and you can set a notional boundary um, where you can track conservation of mass and momentum of fluid that's going through a surface area. This was an analytical technique that was developed by engineers and not by physicists, and it's one that's commonly used. Every engineer that works in computational fluid dynamics likely uses some version of a control volume diagram on a regular basis. And it does take concepts from physics, Like it does take scientific laws, like F equals ma, conservation of mass and momentum, and it embeds them in the study of analysis of a system. But it's a theoretical tool that's tailor made by engineers to apply to physics. You have other engineering abounds with examples like this, finite element analysis, other tools, and these are pieces of knowledge that engineers, types of knowledge that engineers create, that are important. I'll just allude to the last two types of knowledge without giving deep examples. There can be quantitative data, looking at creating wind tunnel testing and figuring out information that can help engineers that design, say, their wings and what the right profile for a wing should be. And then design instrumentalities, which is a category about all the things that an engineer needs to know in order to actually get the job done in a certain sense. And so these are Vincenti's categories of engineering knowledge. I'm very excited. Martin and I have this paper on methods as a form of engineering knowledge that argues that Vincenti's category of design instrumentalities has a hard time capturing methods and design methods in terms of what they are as knowledge bodies. And I do think it's interesting, if you read this niche of literature. I actually might argue that engineers like Vincenti's knowledge categories more than philosophers do. The philosopher of science, Vibo Haux, claimed that the categories that Vincenti comes up with are interesting, but they're not sufficiently comprehensive, doesn't have exclusivity across the categories, and that he's questionable about whether they have sufficient rigor, to be of value. But I think the value of a map of engineering knowledge categories depends upon like what your goal is. If your goal is to come up with a perfect textbook definition of all the varieties of engineering knowledge, which I'm not sure is needed in many cases of engineering, but it also might be impossible to do, then Hauckes's claim might be fairly compelling. And Vincenti himself doesn't acknowledge that there's a lot of blurring and blending across the categories. But if you're caring about like what sorts of things do you need as an engineer that's in an organization building things, what sorts of things do you need to actually learn and uncover on? There's a lot of Vincenti's work that many engineering contexts, including outside the aeronautics context, although more work needs to be done to validate claims outside of there. And I think his empirical cases for almost all of his categories do help to empirically justify the ideas and the sorts of knowledge that these things that engineers are coming up with that in many cases are sort of uniquely their own, um, do exist. And they conceptions of like lay scientific knowledge of like applying scientific laws. They do fall into more classic conceptions about tacit knowledge and know-how, but um, and that's what I'll say about that. So let's now move out to a broader perspective. And so scientific knowledge, isn't it all about scientific laws and the pursuit of universally true positional claims? If knowledge is about getting universally true claims, justified true belief, then one could have an interesting conversation about which pieces of Vincenti's categories of knowledge apply as universally true propositions, and I none. But there's been a lot of debates about what scientific knowledge is, and I'm going to briefly invoke one of my own pieces to help us think about scientific laws, scientific models, tacit knowledge. But I do note there at the bottom that like the late innovation scholar Benoit Godin, Ron Klein, and David Edgerton have done tremendous amounts of work in these areas, specifically reacting against this linear model of innovation. So I already alluded a little bit to the linear model of innovation, and I'm using a graphic here from the philosopher Nancy Cartwright's book, including a graphic that was made by her daughter Rachel Hacking, where linear model of innovation is that you have basic science is the key towards applied science, is the key towards engineering, that's the key towards all these societal outcomes and benefits. And so if you were to rack up all the scientific disciplines,
Can you move the
and
slide? I think we didn't get the image.
okay, let's see. Are you on 14 now?
You got it. Yeah.
Okay. So you've got the sort of implied pecking order of the disciplines in this linear model is that physics would be the source of all new ideas, leading to new ideas in chemistry, leading to ideas in biology, sociology, psychology, and then eventually engineering. And that um, it's also implied that it would be about the application of scientific laws downward in other contexts. And the philosopher Mario Bunge did a lot of work about translating to design rules that I argue against a bit in the piece that I discussed earlier. But there's also implications here. Like if you're figuring out where does innovation come from, it would also imply that like, hey, the seed corn for if you want better progress in engineering practice, you want better planes, for example, that whoops. If you want better planes, that the progress for that is coming from eventually somewhere research in physics. That there's work there that's driving it. So the historians of technology have long argued that this is actually not the case, that much of the learning for new engineering systems comes from work in engineering practice. This very much aligns with a lot of the experiences that I've seen at NASA. You could have an interesting conversation where there's some categories of Vincenti's knowledge, such as the theoretical tools, where you do embed and codify laws from science into an analytic tool, and that's used by engineers. Although in that case, a lot of the like conservation F equals ma has been around for hundreds of years, and scientists would also tell you that strictly those don't apply in a relativistic world, and that if you think about modern physics, it's hard to actually use those equations in a analytically rigorous way. There's a drastic simplification that is technically untrue there. Um, so when you start thinking about this linear model of innovation, that the default epistemology that most people have, if they were to try to figure out like how do we know what we know, there's a bit of uncomfortableness there. And so I mentioned Nancy Cartwright, philosopher of science, who wrote a book called The Dappled World, where she argues that there's in almost every case, if you were to really dig into a scientific law like F equals ma, there's other things that don't apply quite exactly. There's ceteris paribus assumptions about the world. The way in which we end up making laws work in practice is we sort of simplify them in ways to explain things, and it's almost impossible even for the best parts of physics to find universally true claims that apply in different ways. So her book, The Dappled World, is basically dappled in this sense means a sort of messy world where things are a bit complicated. She contrasts scientific disciplines. Her daughter drew it in this beautiful visual of you can have all these scientific disciplines that are connected to different pieces of the world. You can see here where hydrodynamics is connected to the world. You can have some connections between the wave theory of light and the particle theory of light that are branching off just for sort of notional interest and to sort of prime conversation. But you can imagine a world where, like, if this is used to apply and capture engineering knowledge, it actually makes a lot of sense that engineers can have very um, can have their own connections. They might have distant connections to physics from long ago, but they're learning and creating new things to solve the problems that they have to deal with, especially projects that bring people together. So, in this dappled world, if it's not laws that people are discovering, what is it that science discovers or that engineering research discovers? It discovers facts and nuances about the world. It can help you create models of the world, as the philosopher Ron Gary talked about, that could be more or less useful or that represent or do not represent the world. There can be claims about causal powers and regularities, and it can also shape just how we act by giving us insights. But the basis of it is not based on area having primacy over the other. There could be lots of manifold and multi-directional interactions between engineering and science and basic research. And so um, the I think this raises an interesting question then. How should one think about Vincenti's categories of engineering knowledge? Clearly, you can think of some interactions between very long ago aspects of physics and F equals ma becoming embedded in control volume analysis models. If you apply, and this is going to be just a notional, I'm trying to think this through for the first time. If you were to try to apply where do Vincenti's categories potentially come from? I think it's pretty clear. You can see from applied science, if you're thinking about the connection that I just alluded to theoretical tools and to control volume analysis, I think that's clear. I do think there's a whole separate world, and I've seen it in the NASA environment where just management and policy can strongly shape how people actually perform on projects. I think design methods, I think, also falls in there, although that might be more of an engineering activity. I do think truly engineering practice work, the work of actually building systems, can touch upon every one of the categories of engineering knowledge, that you can get new knowledge from practicing engineering in any of these cases. This is a notional schematic, and I hope to pursue this more in future work, and curious for thoughts of others on it. But I do say that like this work needs to be guided. Very proud of a paper that I published on the most comprehensive study that's ever been done to date on where the sources of innovation come from, which was a 1960 study by the U.S. Department of Defense called Project Hindsight that would actually trace out across 20 different weapon systems developments and had teams basically go and study where were the key insights or exploratory events that happened. And you can see based on the time when projects were given the start to go build, a lot of they still had to figure out challenges and overcome challenges as time went forward, but they've been drawing off of years of events and insight that helped figure out where knowledge came from. So I do feel that trying to explore for new pieces of engineering knowledge along the categories of Vincenti's work and trying to figure out where those are coming from could be of great value. But I haven't done that work yet. So I think as I thought about it more, I do think that Vincenti's categories like uniquely more, and I'm more asserting this, proving it in this conversation, but I think more than the knowledge management categories that you might find, say, in Nonaka, they can resonate with engineers. We did have a special panel on engineering knowledge at the most recent FPET Forum on Philosophy, Engineering, and Technology, and had a lot of very thoughtful engineers trying to write down examples of like hidden aspects of engineering knowledge, and most of them did seem to fall under the categories that Vincenti lays forward. So I'm excited to explore work there. I do want to have sort of a final provocation that if you continue on this sort of thought experiment, moving from this sort of linear world to this world where engineering disciplines have their own sort of individual connections towards reality, I do think there's a few high level implications of it that there can oftentimes in the United States, there's the Government Accountability Office will evaluate engineering projects. And if there's any cost or schedule growth, they're like, oh, clearly they didn't plan this out very well. But if you realize so much of engineering knowledge is created after you start building the process, that like even if you've got some idea from physics that's enabling some, like say from quantum mechanics and quantum technologies, there's so many challenges in scaling that up and making it work in reality that expecting there to be challenges in engineering development should be the norm. I think second, that just be very clear that new research needed and new knowledge needed for engineering systems to advance may not have ongoing and sustained ties to traditional research fields like physics, if you believe that. It does raise the question then of how do we actually study where the needed knowledge be coming from, and how do you encourage more of that? But that's an empirical question that needs more work. And I do often feel I've seen people inside NASA the like especially, and there's a lot of challenges of going to the moon. I've helped on the Space Launch System and other activities. There's a lot of people who just assume, well, obviously it's easier to go to the moon now than during Apollo. Like we have so much new technology. Like I think there's this assumption that like help is on the way, that there's advances that have been coming from research in physics that's easy to do, right? Well, it turns out not quite. There's challenges. And anytime you have a new design, there's all the unique things that can happen with that system. And how do you actually know that system well enough to manage it and operate it is just vital. So I'm going to leave it at that. And I think my colleague Martin, as well as Claudia Eckert, Michael Poznich, and Loretta Vandertran, here's some key citations as well as some venues that I strongly encourage people to consider. So with that, thank you.
Thank you very much, Zach. And Martin, I want to give you an opportunity, given that you've been working with Zach, to make any comments you would like to make.
Thank you very much, Zach. I'm not sure what to add. Something that might not be terribly obvious to people who are unfamiliar with Vincenti is just what an incoherent ragbag the notion of design instrumentalities is. I think that this is simply that Vincenti recognized that there's a lot of knowing how to do engineering or knowing how to do design that people possess. And he included this without going into any great detail about what it is or how it works. And Zach and I have discussed with our engineering knowledge discussion partners quite a lot what exactly it does cover, and we're not really sure as to get with Vincenti exegesis. But it is interesting that what Vincenti actually talked about as examples were the kinds of very general problem-solving strategies that people apply when they don't know much about how to solve problems, as opposed to specific engineering problem-solving knowledge or anything that's quote-unquote knowledge intensive. So it's a bit difficult for me to know, or the rest of us to know quite how much to read into that. So we may well have tried reading what Vincenti says about that very carefully and come to conclusions about what Vincenti does and does not include in that he wouldn't agree with.
Thank you, Martin. And I will open up for questions. Sham, if you want to go ahead, please do.
Sure. Thank you. Can you hear me, Asab?
Yes, we
Uh,
can hear you.
Thank you, Zach and Martin, for your presentation and your comments. It's very interesting set of ideas about engineering knowledge. Unfortunately, I have not read Vincenti's work, but I would mention three things that came to mind as I listened to your presentation. One is Philip Anderson, who was a physicist, his 1972 article in Science magazine, it was titled More It Is Different. And there it's basically an introduction. He introduced the idea of complexity science, and it's an argument against reductionism, that somehow you can reduce everything to fundamental sciences, like physics sometimes get the honor, and that you can, like that pyramid did, from psychology to physics. And his idea was that it goes two ways, not just one way. And in a similar vein, Herbert Simon, when he, in his Sciences of the Complexity, he presents the metaphor of a skyscraper. And he says that a skyscraper of science and engineering knowledge is not built from foundations up. It's also built from the top floor down. Both ways, it goes both ways. And otherwise, our ability to build a bridge will depend on our understanding of the spin of the quarks. And the third thing that comes to mind is A more recent book, Gifts of Athena by Joel Mocker. He is an economic historian who also talks about two kinds of knowledge, and he calls them propositional knowledge. I think it's the term you used in your presentation. Propositional knowledge is what we call science, he says, which is answering what and why questions. And sciences are devoted to that. And then he talks about prescriptive knowledge, which is what we call skills and practice, which comes from practice. And again, he emphasizes, like Anderson in physics, Simon in psychology and social sciences, and Mocker in history, he emphasizes the two-way relationship, that science serves as the basis for developing new products, new skills, and but the other way around also is equally important, where skills serve as the basis for science, the practice and skills serve the base of science. And I think your presentation was very interesting because it sort of brings all these three thoughts from Anderson, Simon, and Mocker, more recent work, together in a way. So we think about this process in a bidirectional manner and not a unidirectional way from science to engineering. It just as well from engineering to science. Thank you.
Thank you, Shyam. I think all those thoughts are quite welcome, and I've been listening to some Mokyr work recently. Yeah, and I do think, and it might actually be worth, Martin, for us to just map out which aspects of Vincenti's knowledge can be boiled down to propositional knowledge. I think a control volume analysis is more of a theoretical tool. A design concept is something, it's not necessarily something you can easily boil down to proposition, and sometimes there's a secret sauce of how form translates to function. But definitely like tacit knowledge and other things that are hard to do. But yeah, I do think doing and thinking and engaging in this work and also tying it into working complexity sciences, I think is very appropriate. So I don't have an answer towards things, but I'm just trying to follow. I think this is a worthwhile research lens to use. I do want to see, I wish there was more empirical work in these areas.
Thank you.
Hello, Zach. Yeah. I just have a question relating to how this framework might explain innovation in an academic or a university environment.
So I think
I'll
go ahead, Martin.
let Zach answer this, and then I might add something.
Yes, please.
So there could be many different answers on how do you define innovation. Sometimes people define innovation as diffusion of invention is coming up with a new idea, and then innovation is getting many people to use it. I think that for project hindsight and looking at innovation in engineering systems and allowing engineering systems that can do something new and then getting those to spread and be used broadly, that sort of context I'm most comfortable with. Innovation in a purely academic lab research context, so like especially if one's using a diffusion-based view of innovation, then one might be looking at how can techniques become developed that get shared, or how can come up with a theoretical construct about how the world works that starts to become rapidly shared by others. I do think that for areas of science that could be most provocative for engineering, there are some cases where something like the linear model of engineering can work. So I think work in quantum mechanics these days and understanding how to precisely control relationships. There's been a lot of work in physics that's helping to come with how do you even control this phenomenon? How do you nudge it? How can you use it? It's now becoming the basis that engineers can use to shape their work. But I don't have a work inside the lab is less of my focus. I'm more of thinking about big mega systems.
Okay. A related question is, since you come with a systems engineering background, does systems engineering create a greater possibility for creation of new knowledge? Because you are constantly trying to integrate multiple things in a practical sense. So if one were to use this Vincenti framework and look at systems engineering work, is innovation possibilities higher in a systems engineering work?
Thank you, Sudhir. I think that for Vincenti's categories and the examples that he draws on are typically work on engineering development projects. So it works where engineers are building something new. Anytime you're building a sufficiently complex systems, there are systems engineers on that project. There are sometimes examples of engineering knowledge that aren't necessarily being used by a systems engineer. So the control volume analysis example is one where the systems engineer doesn't need to do that. You actually have your computational fluid dynamics person who runs those numbers, and then they can feed inputs about the systems to the systems engineer. I do think that for complex engineering projects, but the sort of domain that I want to anchor my work in is about the knowledge needed for big engineering projects in general. And I think there's lots of knowledge that's done there. Much of it is in the realm of systems engineering. So I am basically agreeing with you that I think systems engineers are involved in this shaping and bridging and integrating lots of these different disparate pieces of engineering knowledge. I've got other papers underway on thinking better about validation in complex system work, especially also in commercial firm fixed price contracting contexts. And I think that the goal is that and so for systems engineers and also just for any engineers that are working on a big systems project, there's lots of new knowledge that happens there that deserves study, and the way in which that knowledge is used matters. If used well, it has better outcomes for the engineering endeavor and for society, I believe.
Martin, you
No,
wanted to say something? Please go ahead.
just wanted to chip in that the question of what happens to Vincenti's categories when we look at innovation got taken up by Wendy Faulkner, who was science and technology study person in Edinburgh, who wrote a paper in 1994, which she called conceptualizing knowledge used in innovation. A second look at the science technology distinction, which is essentially an expansion of the set of Vincenti categories to try and encompass R&D, which which is a slightly different take. I don't think she's offering much that it challenges Vincenti's main categories, but you do need to appreciate that some things can be fleshed out in a bit more detail, a bit differently, if you're considering R&D. So if you're curious, that's something to look up.
May I put one question here?
Please go ahead.
Yeah.
Mr.
Thank you for
Vaseem.
thank you, sir. So Mike, while I was going through the presentation, thank you so much for this very insightful session. Well, now we are talking about this AI era, and do you feel that the definition of this knowledge creation and these things are to be redefined in this era of AI-driven, AI-assisted knowledge, knowledge creation? Because nowadays the knowledge is creating without any observation or having that feeling of that thing, but it is created by a machine and then you are just validating it. So how do you see this thing, engineering knowledge creation in the present context of AI?
Yeah, and I don't have a complete answer to this. I was peer reviewing a paper recently that had a very provocative idea that argued that engineers have long used black box tools like finite element analysis and Monte Carlo simulation, where you don't exactly know the process by which you're getting an answer, but that there's
Yes.
ways to sort of look at the outputs of the results and to become comfortable with them empirically about them working. I suspect that the types of knowledge needed to build systems will likely be the same, but that with large language models, we might be using them in the process and we might be getting answers that we can empirically attest are accurate, but we may not know how we're getting it.
Yes.
And I think there's just, I didn't focus on it in my talk. I do think that the traditional view of knowledge is justified true belief, that focusing on only propositional knowledge versus this sometimes much more tacit or context dependent knowledge, or just trying to think about causes in a more general that the justified true belief view of knowledge requires that you should, like, there's a believer that there's like a single claim and that you've got good reasons for believing it. If large language models are epistemically opaque and you sometimes can't predict why they come up with the answers that they're coming up with, even if they're accurate,
Yeah.
it could end up in a very awkward situation where we have a hard time knowing. Maybe you
Yes.
have engineering systems that work, but do you really know how your engineering system works? And I've got other. I gave a recent talk recently of like a variety of ways in which you could say that you know whether your system works or not, but it's complex and a lot of that knowledge is distributed. But yeah, it's something that I want to think about more. So thank you for the question, Wasim.
Yeah. So because we are in a very difficult situation in the education scenario, how it is going to be changed, that's a very interesting challenge we are having. Thank you for your response.
Martin, you are a cognitive scientist too. You want to say something along those lines? Okay, I just want to make sure.
I think that what we're struggling with, I think one of the things we're struggling with is our network of concepts for talking about knowledge and understanding and confidence in what we believe. But I'm not sure that large language models, etc., that do things that are really impressive that we can't figure out, as opposed to a bit less impressive that we can't figure out, is creating fundamentally new insights. Except that just how far you can get with statistical regularities astonishes even those of us who've looked at this for a very long time. So, no,
Thank you,
in answer to your question.
Yeah.
Thank you, Martin.
Thank you.
Anybody else wants to say something? Eve, any thoughts?
Sorry.
Go ahead, Eve.
Yes. Sorry. Can you hear me? Or?
Yes, we can
Yes.
hear you.
Okay. No, I discovered actually the Vincenti's book, so I did not know. So it's very interesting. Just I have no special comment. How engineers know, and so I think it's interesting. Thank you for the presentation. So, but I have no comment at that point.
Right.
Thank you. Mm-hmm.
Thanks, Eve. Jack, I have a sort of general question here at one level. The thing is that we are not only bringing engineering knowledge, we are also bringing all other kinds of knowledge in making beliefs as well. It's not to say that it's only scientific and engineering knowledge. There is also the notion of connection to the object. The notion there is a certain connection in a emotional, pragmatic. Like Crows and all talk about the notion of artifact of use and artifact of function. The theory of the artifact as a function and theory as a use. But I don't see them as separate, but they are actually together all the time during the process of engineering. I feel that often we separate them. the actual art and craft of production, as well as the interaction with the materials, is as significant as all the rest of the scientific knowledge we get. After all, our senses can only take us so far, even if we have better and better sensors, we are able to perceive certain things which are not directly perceivable in the current world of sensing. So I want some reaction, especially in very complex systems like moon landing and other things. You're also going by certain intuition, which is beyond any of these directly encodable or systematizable knowledge.
Thank you, Sub. And by the way, I unfortunately have to go in about 4 minutes.
Yeah,
But
okay, that's fine.
I think you know that I'm calling one of my new research initiatives system engineering for societal outcomes, and I deeply think that, especially if you're trying to do either creating an engineering artifact that's meant to help with some sort of societal problem, or you're trying to help change and shape a system, there's so many ways in which users and people are doing their work, and the need for engineers to do that work in conversation with those groups and to have a connection to them beyond just focusing on purely technical things. I do think that when you're doing engineering to get societal outcomes, it's in some ways it's a lot harder than just designing a robotic lunar lander that needs to survive on its own. There, you can do a lot of work with rigorous testing, trying to figure out if something is likely to work. There needs to be and eventually, at some points of the process for a lunar landing, it goes autonomous. And so I think I don't have a brilliant insight at the moment on like theory of a user and tied to theory of function. But I do think that the process of systems engineering, when you're doing it with people involved, and I've even had an example of where I helped NASA do a citizen forum on to inform our asteroid initiative and how to protect the planet against asteroids. And the ability to involve users in that process, and for engineers to find ways to think more deeply about their own values, I think is vital. And your work on we are not all users, I think, is incredibly insightful and provocative and valuable. So I've greatly benefited from your thoughts there. So, but I don't have any other more thoughtful response to your comments now.
Thank you, Zach. I'll let you go because you need to get back to your work, I presume. It's been a wonderful thing. I'm contemplating to have a session where we have a panel, including you and a few others, in one of these lectures as a way to create a form of debate, which could be very nice. I mean, I'll send you some other things which might be useful to you, some work by Stig Anders Pedersen from Riso National Lab on engineering and science, which connects to some of the things you're talking about. With that, Sudhir, I think I'll bring the lecture to close. Thank you all for participating, and it's been a wonderful session. Thank you, Martin, to join us. Thank you for joining. Thank you. Have a good
Next
day,
session,
good evening, good
next session will
afternoon,
be on
whatever.
29th July.
The
session
next
will be
one?
on 29th July.
Okay. Thank you.
Thank you.
Thank you. Bye-bye.